For the physical properties of the acids as any functional group, for the solubility, we are looking at up to 5 carbons because of hydrogen bonding. So more than 5 carbons, as you increase the number of carbons, as the solubility is going to decrease. When I asked about solubility, I need to mention the solvent that we are working with, whether it is water, whether it is methanol. So we have to know what solvent it is, because if it is aqueous, we need to look for hydrogen bonding in there, okay? So here, whenever we have an acid, if we are talking about the solubility in water, then we need to check the hydrogen bonding. And see here, you do have different types, 2 interactions of hydrogen bonding. And you do have a hydrogen that will interact with the oxygen of the water. Or I can have another interaction where the hydrogen of the water interacts with the oxygen of the acid. So here I do have 2 hydrogen bonding interactions. So I would say there that I have 2 times hydrogen bonding interactions. And we know that as hydrogen bonding increases, as the boiling point increases and the solubility increases. So this one I'm expecting, since check always the number of carbons, since here it's a 3 carbons in there, then it will increase the boiling point and it will increase the solubility. So hydrogen bonding in there, 2 hydrogen bonding interaction, and as the hydrogen bonding increases, then the boiling point is going to increase and the solubility is going to increase as well, okay? So the solubility is affected by hydrogen bonding in there, and the boiling point as well is affected by hydrogen bonding. Now, with respect to the hydrogen bonding for the boiling point, we're not working with solvents, so you have to put 2 molecules of the acid that you are working with under each other. First, make sure that they are no more than 5 carbons. So here I do have 3 carbons in there, so I am fine. We check the hydrogen bonding. Let's see how many different hydrogen bonding interactions we have. So the first one is going to be between the hydrogen and the oxygen in there, because this is one hydrogen bonding. The second is going to be between the oxygen and the hydrogen. This is the second hydrogen bonding. And then the third hydrogen bonding is between the hydrogen and the oxygen in there, okay? Between the hydrogen and the oxygen of the carbonyl. So what I have here actually is 3 hydrogen bonding interactions. And this is why acids, they have higher boiling points than alcohols, because they have higher or more hydrogen bonding interactions with each other than the alcohol. Just as a reminder, when we were talking about alcohols, okay? When we were talking about alcohols, let's say if we have these 2 OHs in there, these 2 OHs, we said that there are 2 hydrogen bonding interactions in there. Or actually, yeah, it's you can make it so I can use the oxygen in one, the hydrogen in the other in there, or the oxygen here, the hydrogen there. So I do have 2 hydrogen bonding interactions versus 3 hydrogen bonding interactions. So the more hydrogen bonding your functional group does with another functional group, the higher is the boiling point. So if we have this example where we have multiple functional groups and I ask you arrange them in increasing boiling point, you have to check the intermolecular forces of each one of them and see the one that has more intermolecular forces will be the one that will have the highest boiling point. All of them, they do have the weakest type of intermolecular forces, which is the London forces or the van der Waals forces. Why? Because all of them, they do have a carbon chain in there. And the van der Waals forces or the London forces, these exist between carbons. So all of them, they have van der Waals forces. Now for the dipole-dipole, if you have an electronegative element, then you have a dipole-dipole interaction. And I do have a dipole-dipole here. I do have a dipole-dipole there, because I do have an oxygen electronegative, electronegative. I do have, again, an electronegative in there. So I have a dipole-dipole, but the alkane has no dipole-dipole. So the alkane only has the van der Waals forces. That's it. It has no other intermolecular forces. Now that's it for the ether. I don't have anything else. But for the alcohol and the acid, I do have hydrogen bonding. For the alcohol, I have 2 hydrogen bonding interactions. And for the acid, I have 3 hydrogen bonding interactions. So it makes sense that the acid is going to be the highest boiling point in there. So if I want to go ahead and arrange an increasing boiling point, increasing means from the least to the most, okay? So the acid is going to be the most, so I'm just going to put the acid all the way. And then after that, that is going to be the alcohol in there. So the alcohol, it has a lower boiling point than the acid, but it's still high compared to the ether. And then the least one that has the boiling point is the alkane, which is going to be D. Remember that as the intermolecular forces increase, as the boiling point is going to increase. And what determines the boiling point is the also the hydrogen bonding in there. The functional group that has the highest amount of intermolecular forces will have a highest boiling point in there. Now, if we want to go ahead and include the aldehydes and the ketones, this is the trend for the solubility up to 5 carbons, and this is the trend for the boiling point up to boiling point. It doesn't matter the number of carbons, but the solubility, you have to stick to the 5 carbons in there. So it's always that the acid is the most soluble, and then the alcohol, which makes sense because of hydrogen bonding. Same thing for the boiling point, which makes sense because of the hydrogen bonding. Aldehydes and ketones in there, they are higher the solubility than the ethers, and again because of hydrogen bonding in there, they are higher solubility than ethers, than alkanes. Also, they do have higher boiling point than ethers, than alkanes in there. Okay, so that is for the trend for the solubility and the boiling point.